Hello, we're going to introduce our work, Local Implicit Normalizing Flow for Arbitrary-Scale Image Super-Resolution. Super-resolution aims to recover a high-resolution image from its low-resolution counterpart. There are two main challenges of super-resolution, the ill-posed problem and the arbitrary-scale challenge. However, existing works are not able to solve both problems with a single model. In this work, we introduce a novel framework as a unified solution to these challenges, which consists of a coordinate conditional normalizing flow and a local implicit module. As a result, we are able to generate high perceptual quality images at arbitrary scales. Next, we will introduce the details of our proposed method. To begin with, we define the texture map as the residual between the high-resolution image and the upsampled low-resolution image. Next, we divide the texture map into non-overlapping local texture patches of size n by n. We believe that texture details in natural images are locally correlated without long-range dependency. Therefore, we can model the distribution of these local texture patches independently. In practice, we generate these local texture patches separately and combine them to form a full image. As a result, the target distribution we want to learn will be the conditional probability distribution of these local texture patches. The conditional signals are the low-resolution image, the center coordinate of the patch, and the scaling factor S. Here's the framework of our proposed method. We design a coordinate conditional normalizing flow to learn the target distribution, with a local implicit module offering the conditional signals to the flow model in a hypernetwork fashion. We will first introduce the details of the flow model. The flow model adopts many invertible layers to construct a bijective mapping between the target distribution and the Gaussian distribution. During training time, we map a local texture patch to a latent Z. By the change of variable theorem, the log likelihood of this local texture patch can be formulated as the following formula. As a result, we can compute the exact log likelihood of every local texture patch and optimize our flow model using negative log likelihood loss. During inference time, we randomly sample a latent Z from the Gaussian distribution and generate a local texture patch using the inverse process of the flow model. Here, the variance of the Gaussian distribution is controlled by a sampling temperature tau. A higher sampling temperature will boost diversity of the flow model on details and textures, while a lower sampling temperature will reduce the randomness, causing the flow model to behave toward a deterministic model, generating high fidelity but blurry images. For the internal architecture of a flow layer, we adopt a linear layer and then a fine injector layer. The linear layer performs linear transform on the input, and the affine injector layer will element-wisely scale and shift the input. Note that the parameters of the affine injector layer are predicted by the local implicit module in a hypernetwork fashion, such that the flow model can utilize the conditional signals. Next, we will introduce the details of the local implicit module, which is composed of a Fourier feature estimator and a parameter generator. The Fourier feature estimator will first encode the conditional signals into a Fourier feature. Then, the parameter generator network will generate the parameters of the flow model. For the Fourier feature estimator, we follow the implementation of the CVPR 2022 paper LTE, which encodes the feature vectors, relative coordinates, and cell information into amplitude, frequency, and phase by 3 different networks. These components make up a Fourier feature of a specific coordinate. The Fourier features will be aggregated by our proposed Fourier feature ensemble scheme, which concatenates the weighted Fourier features queried from the 4 nearest coordinates to generate the ensembled feature. The unsampled feature will be passed to the parameter generation network to produce the parameters of the flow model. In summary, by injecting the conditional signals into the flow model in a hypernetwork fashion, our framework can be trained end-to-end to learn the conditional distribution of local texture patches. Next, we will demonstrate the experimental results of our proposed method. Since our method possesses the advantages of both arbitrary-scale and generative SR methods, we compare our method with these two categories respectively, along with ablation studies. First, we compare our model with arbitrary-scale SR methods. Our method achieves better LP-IPS scores with a large margin, which demonstrate that our model is able to generate images with much better perceptual quality. Also, we maintain comparable PSNR performance as the previous methods. Here's the qualitative comparison between our methods and the current state-of-the-art LTE. Our proposed method is able to generate images with a much better visual quality. The images generated by our model are realistic and possess high-frequency details. Next, we make a comparison between our method and the previous generative SR methods. We plot the Pareto front on PSNR and LP-IPS scores since there is a trade-off between fidelity and perceptual quality. From this plot, we can observe that our curve nearly encloses the curves and dots of the previous methods, which demonstrate that we can achieve better fidelity and perceptual quality at the same time compared with previous methods. In addition, we are able to achieve arbitrary-scale SR, which cannot be accomplished by the previous generative SR methods. Third, our model is lightweight and requires less inference time as compared with state-of-the-art generative SR methods. Here are more samples with high diversity generated by our model. The ablation studies demonstrate the importance of the proposed components. The patch-based method generates coherent local textures and greatly reduces the inference time. And the Fourier feature ensemble scheme can further enhance the inference speed. Thank you for your attention.